Let's begin. How are you, everyone? Almost down to the last 3 lectures of class. I finally got the first sample for the 3D printed Larry the lobster, not the model, but the real one. And look, it can clap its hands and do good. So, you know, if you win an award, a student award, you'll get one of those, okay? So you can pass it around, you know, talk to him. And I would like you to submit any award categories if you are so inclined to. I made a few suggestions in the email, in the announcement I sent out. Maybe those are enough, or if you have other categories that you think are more relevant this year to the class, please send me your suggestions. Once I sort that out by next week, then I'll send out another announcement for nominations. You can nominate yourself or one of your colleagues, and we'll do the vote the week after next week. So that last Tuesday, we will do voting in class, and you'll get the award. You'll get a lobster like this, a 3D printed lobster. You'll get an award certificate, high quality paper with a departmental stamp on it, and your name on it. And you can hang it on the wall, etc. Students have enjoyed those in previous years, okay? Today, on my way here, I decided to introduce a new topic, a new discussion in our discussion on boundary value problems. So I spent all day creating new slides for today, and I updated the PDF. So I did not cover this last year or any of the previous years. This is completely fresh. I might have a typo here and there, so I'm hoping you follow with me and you can correct me. But before we get into boundary value problems, there's a discussion that there's something I need to use in boundary value problems, which is called order reduction. That's the thing I'm introducing this year. And I figured I could start by talking about order reduction on initial value problems, which by now we should have mastered with ODE int. So if you recall, or if you notice, so far the only type of initial value problem we've solved are first order initial value problems. dt by dt, temperature, first derivative of temperature, or the SIR epidemic model, those were all first order derivatives, first derivatives, right? But in practice, you might have initial value problems that have second derivatives in time, or third derivatives, or fourth derivatives, and so on. So how do you handle those? If you consider the under the hood discussion, where we approximated the first derivative with a forward Euler or backward Euler, you might be inclined to say, let's approximate the second derivative or the third derivative using second order finite difference and third order, and that's valid. We're not going to study that. However, there's a more streamlined way of doing these higher order initial value problems directly using first order methodologies, and that's called order reduction. And let me show you how it works. So this is an example of the equation of motion for an object or a parachutist or a skydiver free falling in air, okay, subject to gravity, and mass has been kind of incorporated into this, but also subject to some drag. So there's an example I think we did early on about this, but this is the equation of motion. X is the position of the parachutist, so dx by dt is the speed, and d2x by dt squared is the acceleration. So this is nothing more than Newton's second law. Alpha is some drag coefficient, and dx by dt is again the speed squared. So the drag that is being exerted on the parachutist is proportional to the square of the velocity. So when you see this, you're like, oh yeah, this is a time-dependent problem, so it must be an initial value problem, okay? But then, because there's a second derivative, if you think about this, if you were to integrate this analytically, you're going to get two constants, right? And so therefore, you need two conditions to specify those constants. So that's why a second order ODE requires two conditions, two initial conditions. A third order is going to require three initial conditions, and so on and so forth. So the two initial conditions here are that the parachutist is starting from our initial location or position is 0, and the initial velocity of the parachutist is also 0. So those are the two initial conditions. Right now, we have the tools to solve this using a finite difference approximation, but we haven't done it, and it's really quite cumbersome. But we can use ODE int to solve this problem. However, ODE int only works for first order ODEs. But turns out that there's a trick to convert any high order initial value problem, in fact, any high order ODE, to a system of first order ODEs. And here's how it's done. It's called order reduction. It simply goes by assigning new names to the different derivatives. So if you were to call dx by dt, give it another name, call it v for velocity. Okay? So that's an ODE. It says dx by dt equal v. That's an ODE for the variable x. And then d2x by dt squared is really dv by dt, right? Because that's the derivative of this one. Therefore, it is dv by dt. dx by dt is v, so you put v here, and there you go. You've converted one second order ODE into two first order ODEs. Just very simply by reassigning names to the different variables. So in a way, you're solving those in steps. We first solve this one and then solve this one. Now, together, ODE int will solve this just as a system of equations. It doesn't know that these are part of one second order differential equation. It doesn't care about that. It's just two first order ODEs, and you can program those directly into ODE int like we did the epidemic model. The initial conditions now become an initial condition on the first ODE and an initial condition on the second ODE. Now, those are consistent with these, absolutely, because this is still the same. x0 is 0. And this one, v at 0, which is dx by dt, remember, v is dx by dt, equals 0. And that's how you would convert a second order initial value problem into two first order problems. Okay? So now you have just these two new variables, x and v, and you solve the system with ODE int. Okay? Another example, which is the classic swinging pendulum. It has this governing equation for the angle. So you have a pendulum standing here. You move it up a little bit. It has a very thin, massless cord. And then you move the mass or the object attached to it at the bottom. You move it a little bit, and then you release it from rest. Or you could release it at some speed. Right? So the governing equation looks like this for the angle of oscillation. So this pendulum is going to swing. Okay? There's no drag over here, so it's going to swing forever like this. However, that's the equation that governs this motion. And you can also do the same. This is a second order initial value problem with two initial conditions. And you just simply convert it into two first order problems. You go after the first derivative, d theta by dt, you call that v, because that's like the speed, right? The angular speed. And then dv by dt, which becomes d2 theta by dt squared. You just call it dv by dt, right, as a function of theta, minus g over L sine theta. So you have two first order ODEs. Okay? If you had a third order initial value problem, you can convert that into three first order ODEs, and so on and so forth. So that's one technique where you have an initial value problem that's high order. The high derivative is 2 or 3 or 4. You just do an order reduction. You convert it into a system of first order ODEs. We know how to solve those. We did this in the epidemic model. I can do this here again, but I think it's tautological. We've done those. If you really need help to do this, I can send you the notebooks for those. But I wanted to introduce this idea because we will need it in the boundary value problem discussion. Okay? Is this clear? Have you seen this before, maybe? Okay, perfect. Did they teach it in your ODEs course, order reduction? A little bit? Okay. Analytically, though, you saw that. Okay, very good. Great. So we're kind of coming at it from different angles. All right. Now to the second type of differential equations that we want to talk about. That's really the last subject. And that's boundary value problems. Boundary value problems are different than initial value problems in that you do not specify what's the initial condition, the initial state of the system. It really doesn't matter, that initial state of the system. What matters are the conditions on the boundaries of the system. Okay? And If you think about it, described by like this kidney plot, some physical phenomena described by some differential equations here, but what matters is what's happening on the boundaries. And so that's strictly the only way that you're going to get a unique solution for these problems. Sorry, I have to turn off the front lights because it just blinded me. Okay. So the boundary conditions, and boundary conditions in this case must be specified. Now, a telltale indicator for a boundary value problem is when you see the space dimension showing up. Now, in math, they might not necessarily use X. They could use T. They could use Y or Z or whatever. You know, and so it really, it's not very clear when you're thinking about it just from a pure math perspective. But when I think about it from a physical perspective, when I see a second order differential equation with conditions on two sides of a domain, not just at initial time. So if you look at the second order pendulum problem, we had two conditions at t equals 0, the speed and the initial angle, right? The skydiver, we had the initial position of the skydiver and the initial speed of the skydiver at t equals 0. So both conditions were at the same time. So those are not really boundary conditions, they're just initial conditions. Okay? With boundary value problems, you can have a second order ODE, but to tell that it's actually a boundary value, you have conditions on either end of the domain. Now, what is the domain? It's just simply a line, right? Because this is and we're talking one dimension here in space, right? So, classic example that we did at the beginning of the semester is the heating of the rod. So, I remember I promised you, I will show you how we derive that tridiagonal matrix. So we're going to do that in the next in this lecture and next lecture, okay? We will do that. But again, I'm going to come back to this example. This is a rod with fixed temperatures at either end. Okay, so the minute I tell you that, you recognize that this is a boundary value problem because I'm specifying the temperature at both ends of the rods, okay? Now, this rod is subject to cooling or heating because there's some air coming in here. That's not a boundary condition. That's a source term. That's a source of heating or a source of or a sink of cooling. Okay, so it's not a boundary condition. You're not specifying anything on there's no boundary really in the y-axis, right? It's just a source, heat generation or cooling. Okay, and this problem is described by this second order differential equation. It's an ODE because there's only, one independent variable x, and it describes how the temperature is going to vary from one side to another on this rod, subject to the conditions that on this point the temperature is given at TL, T left, or TX left, or whatever TA. And on this side there's also a temperature fixed, T right, or some specified temperature by the user. Okay. Now the equation relates the second derivative of the temperature. There's some coefficients here, HP over lambda A, whatever, we're going to call that as one coefficient. We're going to lump that into one coefficient, times T minus T infinity. T is the temperature, the local temperature on the rod. T infinity is the temperature of the air. Okay, when you study heat transfer, you will learn that this is a convective heat transfer problem. That's the similar equation as when we were boiling the lobster. We had H, A over MCP times T minus T infinity. But we had time dependence over there because in the lobster, we assumed the temperature over the entire lobster or the entire rod was the same. It didn't change in space. It only changed in time. Here, we're assuming it's only changing in space, but not in time. Okay, so here we're going to see a temperature variation over space. Okay? So think of it as like you put the rod, you heated it, and at steady state, it achieved that temperature. It's not changing anymore in time. Okay. And this is the new material I'm introducing this year. And I feel like it is super helpful because this class, as much as it is about teaching you the engineering science behind these techniques, it's also about just showing you the tools that you will need to do numerical methods. So if you think about it from the beginning of the semester, starting with numpy.linspace, numpy.linalgebra.solve, think with me. fsolve, numpy.trapz, scipy.quad, polyfit, right, curvefit, ODE int, and a bunch of others. So we should actually make a list of those and just give them to you. Like, all of these routines are really what you will be using in practice in the future until you hit a problem where you have to dig deeper. But I want to give you something that is similar to boundary value problems. The challenge is boundary value problems break the rule. There's no generic way of doing boundary value problems, except when they are one-dimensional, okay? Then there are some routines that are pre-packaged, and one of them is called solve BVP, or solve boundary value problem, that's provided by SciPy. It's very limited in what it can do, and specifically it can only do one-dimensional problems, okay? And it's not super robust, but it does the job for the most part. And so I decided to teach it this year, but I will also teach you the most robust method, which is the finite difference method. But in that case, you have to treat each problem differently. You have to make a derivation that is specific to each problem you're doing. So you will learn both, okay? But first, I want to teach you the solve BVP routine. Okay, so scipy.integrate provides a library for solving BVPs called solve BVP. Just like ODE int, there's solve BVP. Okay? And solve BVP, at a minimum, requires these 4 parameters. Right-hand side, BC is for boundary conditions, X, and we'll discuss each one of those, and Y0, whatever that means. Okay. So what does solve BVP do? And part of the reason also I never taught solve BVP because it's annoyingly cumbersome to comprehend. Every time I want to use it, I have to read the darn documentation again and get entangled and wrapped up with the complexity of Python editorial documentation people who obfuscate everything they want to write. It's like, say you're getting aspirin or not acetyl salicylic acid or whatever, you know, molecular name you want to call it. Just say aspirin, man, right? So anyway, it's very complicated. So I spent all day trying to simplify this. So we'll see how I did. Okay, so solve BVP solves a system of first order ODEs. Okay, they are going to be boundary value problems. So solve BVP assumes that you're solving the system of first order ODEs on the interval A to B. Okay? So what that means, you're providing a boundary condition at A and a boundary condition at B. Okay? So once you specify that, that tells you you have a boundary value problem. Okay? Now the system of ODEs is given by this vector equation, dy by dx, their first order, equals some right-hand side of x and y. Now notice y is a vector. It's a vector of dependent variables. I'm going to call them y0, y1, etc., and so on. And really what this is saying is that you are solving the following system of equations. y0 prime equal right-hand side for the y0. Let me call it actually RH as 0. Sorry about that. RH as 0. Okay. So y0 prime is right-hand side 0 as a function of x, the entire space domain, and it could be a function of all of the other unknown, all of the other dependent variables. So y0 prime could be a function of y0, y1, y2, y3, y4, etc. Okay? The second ODE would be y1 prime equal right-hand side 1 for that second ODE as a function of everything else, right? So it's a coupled system of first-order equations. Okay? So in practice, what that looks like for us is ODE1, ODE2, ODE3, ODE4. How do we program them? Okay? Now, because boundary value problems, by definition, are described by at least second order and higher ODEs, because you need at least 2 conditions, right? Because there are boundaries. There's 2 boundaries. Then that necessitates that for every boundary value problem you're dealing with, you have to do order reduction to convert it to a system of first order ODEs. Turns out you can do order reduction on boundary value problems as well as initial value problems. That's why I introduced order reduction first. All right, so let's talk about the specifics here. And again, this might seem esoteric or like kind of confusing. Once we program an example or 2 by hand together, it becomes clearer. Okay? The hardest one is going to be BCs, right? I'm telling you from now. Right-hand side, just like ODE int, right-hand side is a Python routine that returns the vector of right-hand sides for your ODE system. Right-hand side 1, right-hand side 2, right-hand side 3, just exactly as we did it with ODE int. Okay, no mystery there, right? However, it changes the form a little bit. The function call, the routine call for the right-hand side in this case, has to look like x comma y. That's by definition. Because solve BVP is going to call right-hand side, is going to give it the x values. Those are the location on your line, okay, on your domain, and all the y values, y0, y1, y2, y3, etc., and so on, okay? So then your right-hand side gives you this. This y is a vector containing y0 at all x points, y1 at all x points, y2 at all x points, and so on, okay? I say this like this. This is a vector containing the solution variables, y0, y1, etc., at all points. Remember, y0 is the first ODE, y1 corresponds to the second ODE, and so on. Okay, this is the hardest one. BCs stands for boundary conditions. This returns boundary conditions in residual form. Do we remember the residual form? What is the residual form? Move everything to the left-hand side. So if I tell you t at x equals 0 equal 100 degrees, what is the residual form? T at x 0 minus 100 equals 0. That's it. That's all there is to that residual form. Okay. But that doesn't stop there. Okay, it doesn't end there. Interestingly, the way they programmed this is that BCs has to take a very specific input form, and by definition, that's what they require us to do. We have to define BCs as a routine that takes in YA and YB. These are values passed on by Python. Okay, I'll explain to you what they contain. YA represents the boundary at the left end of the domain. It doesn't represent any of the variables. It represents that boundary. YA is the boundary at A. So any conditions at A, you have to use YA to implement them. YB represents the boundary at the right-hand side, so at the end of the domain. So any boundary condition at B, you have to use YB. Okay, so what the heck? How do we do that? Okay, here's an example. Turns out that YA and YB are actually arrays. And the index of the array tells you if it is the actual value of the initial ODE before you reduced it. Before you reduced the ODE, you had some variable. Could have been temperature, pressure, U, and whatever. So you still retain those conditions there, and you apply the conditions on that initial name of that variable, okay? But then, YA0 gives you access to directly to the dependent variable in your initial ODE, okay? I didn't call it Y. This could be U or V or whatever initial name of the variable before you reduced it. But sometimes you might have a derivative boundary condition at A. So you're specifying the rate of heating instead of the temperature, for example. Then you need a boundary condition on Y prime. How do you get to Y prime? You call YA1. YA2 gives you Y double prime at A. YA3 gives you Y triple prime at A. So that's the idea here, is that YA gives you the boundary at the left point. The index of YA gives you the order of, or which derivative it is that you're applying this boundary condition on. Same thing with YB. YB gives you the boundary at B. And again, YB at 0 gives you access to set the boundary condition on Y, the initial dependent variable in your original ODE, not the reduced one, at B. And then if you have boundary condition on the derivative, which you could, or the second derivative, and so on, you access that through the index of this. Okay? I told you this is the hardest part. That's the part that always confuses the heck out of me and everyone I work with. But once you write it down, you're like, oh, okay, it makes sense. You write it once, and you forget about it. Okay? Well, once we do the example, it becomes clearer. All right. That's the hardest part. Next is x, which is just the sequence of points on which you want to solve this problem. So by definition, then, that specifies the endpoints of your domain, x from A to B, right? That's what it goes from. So when you specify x, this array with linspace, for example, right, then Python figures out that the boundary conditions ya is applied at this point and yb is applied at that last point. And finally, y0, you need an initial guess for all your dependent variables at all points. Why do you need an initial guess? I just told you that boundary value problems do not need an initial condition. Well, be careful. Distinguish between initial condition and initial guess. When did we ever need an initial guess? When we were doing nonlinear solvers, right? Or when we were doing iterative solvers. Turns out that solve BVP internally is doing some form of a nonlinear optimization problem called the shooting method, which I do not recommend anybody learn that silly method. Anyway, that's what it's doing. That's why it needs an initial guess. How do we set the initial guess? I'll show you once we start solving these problems. You could just set 1 or set the value of like the ambient temperature in your problem. That's about it. Okay? Now, how do you access the solution? Once you run solve BVP, you dump this into some variable. I called it sol. And so here's what, from the documentation of Python, I don't know what is going on with those people, but it says it returns a bunch object. So apparently now the word bunch is a programming concept. You know, I could understand tuple or array, but now bunch is also a programming concept according to Python people. That's literally what the documentation says on SciPy, that solve BVP returns a bunch object that contains a collection of information about the solution. What you really need are your x values, which you already have input, or you can access them from sol.x, or you can start accessing your y0, y1, y2, and so on like this. Sol.y0, sol.y1. It gives you the values at all points x for the first dependent variable, for the second dependent variable, and so on. Whew. OK. Let's do some examples. We'll do 2 examples, OK? We'll do 2 examples, and we'll be done with solve BVP. From your perspective, you'll most likely be using solve BVP until you cannot use it anymore, OK? So that's why I wanted to give you that solve BVP. OK, here's an example. And if you're taking ODEs right now, you might have seen some ODEs like this. So this is one way for you to verify and explore the solution. If you're getting analytical solutions and we're like studying these ODEs, please try to use this on things that you're learning. Right? I didn't have time to do animations here, but just go with me from top to bottom, left to right. OK, so we start at the upper left corner. Our ODE is given by u double prime plus 9u equal cosine x. OK, so you could tell this is a second order ODE. OK, is it a boundary value problem or initial value problem? Well, I could tell I have two conditions. I need 2 conditions because this is a second order ODE. But those conditions are specified at 0 and at pi. OK, so that tells me this is a boundary value problem. I'm anchoring the values of u, 1 at 0 and 1 at pi. In fact, at 0, I'm anchoring the slope of u, not the value, the slope. So u prime at 0 is 5, and u at pi is minus 5/3, and the domain is from 0 to pi. So it tells me it's a boundary value problem. If I want to use solve BVP, I need to reduce this to a system of 2 first-order ODEs, because solve BVP only solves a system of first-order ODEs. All right, so let's do that. Now I'm going to change the way I did reduction here, and this is more systematic. OK. So I'm going to call my dependent variable u, I'm going to call it y0, because I want to be consistent with my nomenclature, y0, y1, y2, and so on. All right, just to simplify things. So let's call u, let's call it y0. And u prime, we're going to call it y1. All right, now see what happens. If you differentiate this, that's the next step. You take these and differentiate them. So y0 prime is u prime, but u prime is y1. So that's y0 prime is y1. That's your first ODE. OK? Now y1 prime is u double prime, right? And nothing magic here, just taking the derivative of the entire equation. So y1 prime is u double prime, but notice I have u double prime up there. So if I take my ODE and take this and plug it up there, I get y1 prime, that's u double prime, plus 9u, but u is y0. So you get 9y0 equal cosine x. And there you go. I have my two first order ODEs. y0 prime is y1. y1 prime is minus 9y0 plus cosine x. Seems like magic. It's just reassigning names. Okay? If you're confused about it, always start by calling your original dependent variable, call it y0. Its derivative, call it y1. Okay? And propagate this, take their differentiate those, and then substitute. So you get your two ODEs. Get some water. Okay. Now on to the boundary conditions. Solve BVP doesn't care about the boundary conditions, and solve BVP don't care about the reduced form. It works directly with the original variables, u prime 0 equal 5, and u at pi equal minus 5 over 3. So what that tells me here is that it tells me that the first derivative at point A, which is the left side of the domain, is equal to 5. All right? So that's ya, that's at boundary condition at A. The first derivative, so I choose index 1, equal 5. In residual form, that's minus 5 equals 0. Okay. For this one, u at pi equal minus 5 over 3. So this is point B. That's the right-hand side. So I need to use yb, but I'm using the 0th derivative, so no derivative. So yb 0 plus 5 over 3, that's the residual form, equals 0. Those are your two boundary conditions. Get your notebooks, and let's do this in Python. All right. Solve BVP example. So what we will need in this case, I'm going to copy paste everything from a previous notebook. But from scipy.integrate, I need solve BVP. Okay? Give you a minute to catch up. And maybe I'll move my slides over here so we know what we're doing. Okay. So I'm trying to first implement these two here, right? And if you go back to solve BVP, what I need first is this right-hand side. So my right-hand side needs to be defined as x comma y. And I'm going to assume that y is bringing in the dependent variables in that order, y0, y1, and so on. Okay? Let's go back to this one here. Luckily, I wrote everything in that order, y0 and y1 prime. I'm going to go and say define right-hand side x, y. Now note, y is an array of dependent variables, y0, y1, etc. Okay? All right. Now my y0 is going to be located in y0, and my y1 is going to be located in y1. That's the simplicity of having to use this nomenclature. I know we used phi, we used whatever. Let's just use y for now. It's wise. Okay. So now I need to return these two right-hand sides. The first right-hand side will be y1, and the second right-hand side is minus 9y0 plus cosine x. Okay, so return np.array, just like we did with ODE int. I'm going to return y1 in the first right-hand side. So now Python is going to say, oh, the client or the user is solving y0 prime equal y1, and y1 prime equal to minus 9y times y0 plus np.cosine x, right? There you go, minus 9y0 plus np.cosine x. Okay? That's it for the right-hand side. Pretty simple. If you follow the strategy, call the dependent variable, call it y0, its first derivative, call it y1, its second derivative, call it y2, and so on, and start substituting. Second order ODE converts to 2 first order ODEs, third order converts to 3 first order ODEs, and so on. Okay? Now let's define the boundary conditions. Define BCs, and from the definition of solve BVP, what they want from us is, what they provide us with is YA and YB. Okay, go figure why they named them that way. Maybe I think there's like no better way of doing it, so they chose the worst possible way except for all the others. So whatever. Okay, it just works. All right, so what are we going to return here? It just magically works. Our first condition is going to be on the left point, ya, the derivative of u, so u prime at 0 minus 5 equals 0. So you just return ya1. So that's u prime at 0. 1 is the first derivative. Ya means that this is at the first point, at the left end point. Okay, ya1 minus 5, and the second one, it's in residual form, so of course it's equal to 0. Okay, and the second one is yb0 plus 5 over 3. So yb0 plus 5 over 3. Okay, I'm going to put 0.0 over here. Okay. Ariana and Ainsley are like, of course, I wish you taught us that last year, right? Okay. So now let's say we want to solve this over 100 points on the domain, which is just 1D. It's a line. So we'll declare a lin space from 0 to pi. Remember, our ODE was defined on the interval from 0 to pi, okay, with 100 points or 200, whatever. And now for the initial condition. So initial condition. Now think about this. I have two dependent variables, y0 and y1. Each one of them, I need an initial condition over 100 points for each one, right? Because I have 100 points, or I could put 200 points. So in other words, I have two dependent variables. Each one has n initial guesses. Okay? The way solve BVP expects you to do this is a two-dimensional NumPy array. Okay, so let's do that. It's going to be, let's do it as ones of size 2 times n. So you have two dependent variables, n initial guesses, right? If you don't like this, print y0. So let me put 10 points here. y0 is for this initial condition, or let me call it IC. Okay, let me call it IC, so you're not confusing this with y0, the dependent variable, okay? So IC, the first row or column, whatever Python is doing there, that first row contains the initial guess, actually not IC, it's not an initial condition, it's an IG. It's not Instagram, it's initial condition, initial guess. IG contains a two-dimensional array. The first row contains the initial guess for y0. The second row contains the initial guess for y1. Make sense? Yes?
Why do we have to put two parentheses around the
Because that's kind of the size of the array, right? So if you need an array, just like you do, so if you did np.ones of size 4, that gives you a one-dimensional array of size 3 or 4, right? To do a two-dimensional array, you put a tuple in parentheses, okay, 2, 2, for example, right? So that would give you, okay, or 2, 4, right? Now, if you add one more, it gives you a three-dimensional array and so on, okay? That's it. So Davin is asking, what do we mean by this parentheses? It's the dimension of this array. This is an array containing 2 rows and n columns, or 2 columns and n rows. Let Python worry about that. It really doesn't matter. This is not really a matrix. It's a two-dimensional array, 2 rows, 2 columns, or 2 columns, 2 rows, n columns, or n columns, n rows, and 2 columns. It doesn't matter. Python is going to figure that out. Finally, we can call this solve BVP, and we will give it the right-hand side, the boundary conditions, the x locations, and the initial guesses, okay? And then we can plot it. blt.plot. We'll do sol.x or x, doesn't matter, and sol.y0. Okay, so y0 is actually u, right? So that's what we're after, right? If you're after, when you solve this ODE, you're after u, not u prime or u double prime, right? So I don't really care much about y1. It might be important, but I really care about u. That's what I'm trying to solve. So I can just get it from y0, and if you run this, you get this oscillatory system. You can get the analytical solution for this one. It is correct. Yes? Yeah, oh, sorry. Yeah, okay. Yeah, so sol, I want to show you this. It's a bunch object. So let me scroll to the bottom. See, it's a sol. It returns a bunch object with the following fields. So it's a collection of items, I guess. So bunch is now, a formal word. All right. Put 100 points. Works as well. Gives you a nicer, smoother solution. Did you all get this? Okay. Now this ODE has hardly any intuitive meaning. That's the stuff you might learn in a pure math class. Where, okay, solve these random ODEs. There's no intuitive meaning to them, but at least now we know the mechanism to solve them. Do you have a question, Darren? There you go. It's the same thing. It stores a copy of it. Okay. Yeah. The idea is if you were to hide this in some obscure routine and just return sol, right? Sol contains all the info you need to reproduce the solution, right? Yeah. But it's the same thing. So sol.x or x is the same thing. And I mentioned this here that sol.x array is the array at which solution was evaluated, same as this x input, okay? All right, so now let's do a more intuitive problem. We're going to go to this heated rod. On the left and on the right, at x0 and x equal L, or A and B points, okay, the temperature is known, and the heat equation is given by this second order ODE, and I'm going to just lump all of those parameters, HP over lambda AC, into one coefficient. It's just the effective heat transfer coefficient. Okay, if H is high, it's going to equalize the temperature much faster. If you remember our first few lectures when we did the tridiagonal matrix, if H is high, it's going to equalize the temperature very quickly across the rod. If H is low, it's going to resist equalizing that temperature throughout the rod. Okay, so that air blowing at T infinity is either going to quickly propagate throughout the rod, or is going to have a hard time propagating. We're going to change the values of H to understand, to explore this. But first, we need to do order reduction. So this problem, we will solve it next with finite difference method. But I want to show you how to solve it with solve BVP. And unfortunately, you can only do it in one dimension here, like this. That's it. If you want to do the heat in a two-dimensional plate or in a three-dimensional block, like you will do in heat transfer next semester in the fall, solve BVP cannot help you. Okay, so that's the limitation of it. All right, so let's do order reduction. Like we did, I'm going to call T as Y0, and T prime, I'm going to call it Y1. Okay, just standard way of order reduction from now on. Right? You take the derivatives of those, you get Y prime 0 is T prime, which is really Y1. So that gives you your first ODE, reduced ODE, first order. Your second one comes from the fact that Y1 prime is actually T double prime. So if you go back and substitute into the original governing equation, you get Y1 prime equal H Y0, which is T, right, minus T infinity. So now you've converted the second order boundary value problem into two first order ODEs. Boundary conditions are applied directly on the original variable on T. So this is telling us that T left, or TA, T at x equals 0 is some value called T left, and T on x equal L is T right. So the residual form is YA 0, so that's the boundary condition at A, 0's derivative, minus T left is 0, that's residual form. Boundary condition at B, so that's YB, 0's derivative, minus T right is 0, residual form. That's it. All right? Let's do it. Okay, so now we do the heat transfer problem. Heated rod. Define right-hand side heated rod. And this will be xy, okay, just like we did here, xy. I can actually just copy and paste. Y0 is y at 0, and y1 is y at 1. And I'm going to return an array containing the right-hand sides for this system. That's y0 prime equal y1. So I got y1 over here. And for the second ODE, it's h times y0 minus t infinity. Okay, so I'm going to put h times y0 minus t infinity. All right, so I'm going to need to declare some variables. You can't pass parameters with this equation. If you pass with solve BVP, it's a whole long story, but bottom line, you cannot pass parameters unless you're optimizing those parameters. So you have to kind of declare them within the subroutine somewhere. Either hard code them or just make them locally global in the cell. Okay, so h is equal, let's say, 10, whatever that number is, and then we'll change it as we develop the solution. And T infinity, so that's the air blowing. Let's do it 500. Okay, I need T left and T right. So T left, let's say at 300, and T right is equal 300. Okay, so equal temperatures at both ends, but we're blowing hot air at the rod. So what do we expect? We expect the solution to have temperature anchored at 300 on each side, and then, going up in the middle. Now, depending on h, is going to be either almost a triangle, okay, or almost flat like a rectangle. Okay, if h is high, I hypothesize that it's going to be almost like flat. If h is low, it's going to be almost like a triangular shape. Okay, in fact, like just two straight lines. Okay, all right. So that's the heated rod. So for the boundary conditions, I have YA0 minus T left is 0, and YB0 minus T right is 0. Couldn't be easier. So YA0 minus T left, and YB0 minus T right. Okay, great. Now let's define our domain. I'm going to put 100 points. X is mp.lin space. Let's go from 0 to 1. Length of the rod, okay, with n points. And our initial guess is going to be, okay, what do you think we should put for the initial guess? Well, the temperature is going to be between 300 and 500, right? So any number, any one of those two numbers or anywhere in the middle is going to be a reasonable guess, okay? And you don't have to give it a shape, just pick a fixed value for all of them. So I'm going to pick 400 or T infinity. I'm going to pick T infinity. So I'm going to say this is going to be T infinity times MP dot ones of size 2n, right? Why 2n? Because you have two dependent variables, y0 and y1, and you have n points. So you need an initial guess for every point for each one of those dependent variables. Okay? And if you're in doubt, print it out. Print IG. Okay? 500s everywhere. Okay? Good. All is well. Right? Shall we solve it? Sol equals solve BVP. I'm going to give it right-hand side heated rod. We need to give it the boundary conditions, BCs. This is going to override the name we declared earlier for boundary conditions, okay? And X for the domain values and your initial guesses. Okay? It did something, so let's plot it. plt.plot sol.x or x and sol.y0. That's what matters to me, the temperature. Okay. So if you're still catching up, who has the lobster? Oh, I'm going to give it to Kyle's son to play with for a second. Okay. Hey, dude, can you promise to give this back to me at the end of class? You can play with it now. What do you think it sounds like? Maybe it eats food? All right, what do you think, guys? You got it? Okay, play with H now. Put a small value for H, put a large value for H. Let's see what happens. So this is what I got. Starts at 300, ends at 300. Very good check, sanity check, that we nailed the boundary conditions. This is the exact same problem we solved in the beginning of the semester, where we had these large tridiagonal arrays. Remember? Do you remember that? This is the exact same problem. It's using a different method. It's using a built-in routine in Python. Okay? But it's the same problem. Now, play around with the boundary conditions. Play around with H. What do you see?
So this is like the temperature profile across each point of the rod.
Correct.
Only at a specific point in time, right?
It's at steady state. Yeah, so suppose you brought this rod from the freezer, a spatula from the freezer, or a sausage, or whatever, right? You put it and you fix the temperature on both ends. It starts heating, you're blowing air at it. Then after an hour, right, it's going to reach a steady state. The temperature is not going to change anymore. It's going to look like this forever. So that's what we're looking at. It's steady state.
If we
Yeah.
were to look at the change over time,
It becomes a PDE. It becomes a partial differential equation. Then you have to combine ODE int with the techniques I'm going to show next. You can't combine ODE int with solve BVP, but you can combine them with with the finite difference technique, okay? Yeah, but that would be the natural step next, okay? All right, so what happens if I change H? I'm keeping T infinity as is. I'm changing H to 1,000. All right, what is going to happen? Oh, look at that. Correct, right? That's what we expected, that if H is high, you're going to equalize the heat much faster. It still has to drop to 300 at the ends because that's what the boundary is forcing it to do. But in the middle, that heat transfer coefficient propagated the temperature very quickly, equilibrated that very quickly. The opposite is true when H is small. So when you do e to the minus 5, for example, it barely changes. Okay, so this is 300, 300, right? So this is plus 3 times 10 to the 2, okay? I know it's weird kind of Python putting 0, but this is 0 plus 300, okay? So it's 300, 300, but then in the middle, the temperature is barely even getting close to 500. So it's almost like a straight line, right? Because 300 and 300, what is the answer if h is 0? It's going to be a straight line, a horizontal line, right? This will be more visible if we do t right, let's say we do it at 400. It's going to look almost like a straight line between 300 and 400 because h is very small. So when h is very small, again, we did this exercise when we talked about the heat equation early in the semester. If h is small, it's almost like the right-hand side is 0. So you just get a second derivative of temperature equals 0. The exact solution is straight line. Okay? Exact solution is straight line. Okay? That's it for solve BVP. All right, we got it. Okay, let's take 5 and we do finite difference methods after that. Okay?
Because it always like kicks me to Google Chrome, so I wondered if like, oh, did they have like a cloud storage for it? Oh. Like he's just exercising by himself? That's awesome. Good job. All right, all right, all right. All right, develop a differential equation for this process. Good job. 10. All right. You know what that is?
Missing from post. So it's not allowing you to even solve anything?
No, it works fine. It
Ah.
won't let me save.
Oh,
And I
In
can
your
like,
local.
open a new notebook.
you probably have to restart your,
Yeah, I just
yeah. So it's this. It says it's disconnected. So that's kind of the stack trace of what's going on.
Am I able to just copy the whole thing?
You can leave it open, kill this, and then restart it, and then copy paste. So let's see if you do make a copy.
It doesn't do anything.
It doesn't do anything. Yeah.
Stuck.
Yeah. Ouch. Go, 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 go.
What happens when I do this and copy?
It might copy it, but it will leave this as this if you kill the, yeah. So
How do I kill it?
so if you so go back to terminal and just kill it, shutting down all 12 kernels. Okay, and then we start a new notebook, and then Jupyter notebooks. That's the same thing that Anaconda would do.
Okay, I was gonna say.
Okay, so all right. So now, let's say you create a new. Let's say delete me. Okay, import numpy as np. It's saved it. Okay.
So now I just,
All right. So yeah, the other one is a different kernel. So say OK, but then you have to copy to the other ones. And you can copy each cell at a time, I think. All right. Let's resume. So prepackaged routines, the reason I didn't teach solve BVP, it's because it's very limited. And I tried to put this in the statement, like these prepackaged routines for boundary value problems are not robust, are only effective for 1D problems. So only on a line, you're solving the problem on a line, okay? And what if you wanted to solve the heat transfer problem, for example, in 2 or 3-dimensional domains, right? So solve BVP is going to be useless. You have to derive the equations like I will show you next, okay? Solve BVP, in fact, uses a method called the shooting method that used to be taught a long time ago in numerical methods. Since I took over, I don't teach it. Nobody hardly ever teaches it. It's very limited. It's nice and interesting, but that's about it. It's not going to be robust for any serious computing, okay? And only works for 1D problems. On the other hand, finite difference methods, which we had exposure to a few different times, more lately with ODE int under the hood when we did forward Euler and backward Euler, right? When we took that derivative and applied numerical calculus on it. So that's if we adopt this approach on boundary value problems, then we have a very robust mechanism of solving those problems. It's a little bit more tedious, but it is very robust. It applies to any sort of new and different boundary value problem. There's a lot of details that go into that, okay? So they're more robust, but they cannot be prepackaged, and each case must therefore be derived separately. So for each problem, you have to re-derive the system of equations independently, separately, okay? So we will take that heated rod example again, because that's kind of one of the simplest and most applicable to chemical engineering, because there's an analogy between heat and mass transfer. As you study mass transfer and you derive the equations for mass transfer, they look exactly the same as the equations for heat transfer. It's a diffusive process. Information is propagating between molecules talking to each other. All right, so this heated rod, again, the setup, you know the temperature, you fix the temperature at both ends, okay, left and right, and you're heating the rod somehow with air or whatnot, right? So that same equation. This H is a heat transfer coefficient that tells you how fast the heat propagates inside the rod. So I had a little activity here. I'm not going to do it. So the first step to do this with the finite difference approach, like we did with the initial value problems, is to discretize the domain, split it into x points. We did that with solve BVP. We did that with ODE int, right? We did that when we did the forward Euler. So we're going to do that more explicitly now with the boundary value problem. So we are going to split this into a number of points. They could be equally spaced. They could not be equally spaced. But if they're equally spaced, it's very common to have them equally spaced. It has some unique properties when they're equally spaced, but they don't have to. Okay, we're gonna assume that they're all equally spaced, and the spacing we're gonna call it either h or delta x. And when we did time integration, we did h or delta t. Okay, so delta x is simply the spacing between any 2 points, and those points, each one of them has an x value. Okay, so starting at x equals 0, and then x1 equals 0, indexing here is shifted to 1 again. So x2, x3, all the way to any point in the middle, xi, neighboring point to the right is xi plus 1, xi minus 1. So we've seen this, okay, when we did numerical calculus early on in the semester. Next, we are going to assign a variable for the temperature value at each of those points. Again, if you remember the early lectures on linear solvers, we had an exposure to this example. The only thing different now is I'm going to take you behind the scenes to understand how we derived those tridiagonal systems, okay? It's really not that complicated. We know the temperature at the left point, call that T1 equal T left, and then everything in between is unknown, T2, T3, all the way to Tn minus 1 if you have n points, and the rightmost point is specified, Tn is equal to T right. So in a way, you already have two equations here, an equation for T1, which is given to you, and an equation for Tn, which is given to you, but everything else is unknown. And if we want to solve for the temperatures that are unknowns, we need an equation for each one of those temperatures, okay? Kind of obvious. You have n minus 2 unknowns, you need n minus 2 equations. Okay. So now my question to you, based on the initial value problem discussion on Tuesday, when we did forward Euler, etc. Now the question, is the governing equation, this T double prime equal ht minus T infinity, is it valid at all of those points? No. No, I gotta know. Who says no? Tanner? You gotta come up here and explain yourself, young man. Who says yes? No. Okay, it's gonna be a no. It's been voted. What do you think? Is that, okay, so let me ask you this. Is this ODE valid on that rod? Okay. Are those points part of the rod? So it's going to be valid at those points? Yes. Of course it's going to be valid at those points. Of course it is. It's only those points are only a subset of that rod. Okay? So that's the entire domain of that ODE, right? From left point to the right point. That ODE exactly and continuously is going to be valid at any one of those points. Okay. So indeed, the governing equation is valid at all of those points. Why do you not agree?
Well, when you look at derivatives on a line, at the endpoints, derivatives don't apply. That's what I was thinking.
But it's specified. So it's specified at those points, right? At those endpoints. If your concern is that the endpoints, we don't apply that equation at the endpoints, right? Yeah. But everything else in between, from like left point minus and left point plus and right point minus, it's valid, okay? All right. So then, at point 2, the equation is d2t by dx squared at 2. It's ht2 minus t infinity, right? I'm just applying that ODE at that specific point. Agreed? And the temperature at that point is T2. At T3, you have the second derivative at point 3 is equal ht3 minus T infinity, and so on, right? And I told you we need an equation for each one of those points, right? So that's the first step in that direction. Okay? The problem is that I still have a continuous equation here. Now, this is solvable exactly in this case, but when it's nonlinear, when you have sine t to the power 4 and whatever, is going to be, you're not going to be able to solve that analytically. Okay, so you need to solve it numerically. So then, based on what we did with initial value problems, what do you think is the next step is? The next step is in trying to solve this numerically. So now we have an equation. It's still continuous, but we do have an equation at each one of those points. But I still have an issue here. I don't know how to compute that numerically. So what do we do? What did we do with forward Euler? What did we apply on the first derivative with forward Euler? Okay, you get a lobster if you answer the question. A real lobster. So how do we convert a continuous derivative to something that relates points to each other, right? Numerical differentiation, right? That numerical calculus where we took a continuous derivative, approximated it with a central, with a finite difference scheme, forward or backward, right? So the simplest approximation you could do here is to use a central difference formula. Okay, so now you're going to have to go back through your slides and try to fill in the blanks, okay, as a group. Okay, come on, let's do some activities. I know it's the end of the semester. There's like 2 more lectures. You're all doing some other stuff on your computers. But that's fine. You only have like 3 more lectures with me, and then you'll forget me forever, okay? Don't you want to use that valuable time? So remember, go back to through your lectures. How did we approximate this derivative at point I? Ainsley and Ariana told me you guys did so good on numerical calculus. So if you did so good and you can't remember, then you're all going to get 0 on that homework. Or you do remember. Okay? Yeah, think of dimensions. What are the dimensions of this d2t by dx squared? It's Kelvin over meter squared. So what are the dimensions of the discrete formula? Yes, exactly. So that's how you remember if you have delta x or delta x squared or delta x cubed, right? Okay? So I know the runts got it. Okay? Rotrascals? No? No? Max? No? No? Go back through your slides. How do you approximate a second derivative? You just did it in homework, what, 8? Right? It was much harder. Okay. Yes, Aaron? Ti at point I.
Fi plus 1 minus 2 Fi plus Fi minus 1 over delta x squared.
Correct. But instead of f, we have t. Right? Okay, that's it. Just a second derivative approximation. Ti minus 1. So that's the point to the left. Minus 2ti, that's the point in question, plus ti plus 1 over delta x squared. And we already know that this, on the right-hand side, we have hti minus t infinity because that equation is valid there. And that's it. Now we have an equation that is algebraic in nature. There's no derivatives in it. It's just values, direct values of the variables. There's no, the whole point of solving in ODE is to get rid of the derivatives. Is to integrate that ODE so you have the actual value t in terms of t. Here we're doing it numerically, an approximation to that second derivative. Right? So what happens when you do this? Okay, let's multiply by delta x squared everywhere. And this is a linear equation as far as we can tell. There's ti minus 1, ti plus 1. What do? We put all the unknowns on the left-hand side, which are ti minus 1, ti plus 1. Right? And put everything we know on the right-hand side. Okay, look what happens now at that point. You have minus 2ti and minus h delta x squared ti, which comes from the right-hand side. Okay. So now at any point I, remember this equation comes from approximating the ODE. We approximate the entire ODE at point I. Okay. This is not the equation at I minus 1 or I plus 1. This is the equation at point I. But it depends on ti minus 1 and ti plus 1. That's called coupling. And of course, if I want to know if I am at point I, how do I adjust my temperature? I need to know what's happening at my neighbors, right? Before me and to my left and to my right. Okay, so we're like holding hands. We're like, if they're wiggling, I'm going to wiggle with them, right? It's not like I have ti independently from everything else. That's the coupling, and that's a good thing because that's how you propagate the heat across the rod. Okay? So now we have all the ingredients to solve for the unknown quantities. We know T1, we know Tn. Now we have that equation, generic equation for any of those interior points. Okay, T2, T, etc., etc. Now I want you to explain what to do next and why we have all the ingredients. What do we do next? So this is the recipe at any one of those points. This is the equation at any one of those points. So now what's the next step? What do? Okay, so to get to the matrix, the matrix represents what? A system of linear equations, right? Okay, so what are those linear equations? So you take this equation. What happens if you take this equation and apply it at I equal 2, I equal 3, I equal 4, all the way to I equal n minus 1? What do you get? Start writing it down. Write it at point 2, write it at point 3, then you're going to see a pattern, and then dot, 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 all the way to the last point, to point n minus 1. You guys write it? Okay. T1 equal T left, T1 minus, dot, 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 and then just the n minus 1. And since you said the word matrix, I expect you to write it in matrix form. Okay. So if you cannot see this, this is a system of linear equations. To see the system, I just told you to write it at point 1, point 2, point 3, all the way to point n. Okay? So here's how it's done. At point I equal 1, you have T1 equal T left. That's given to you. The equation doesn't apply there. It's specified. Okay? That's the point that Tanner was trying to make. So he's correct. It doesn't apply at those points because that's you don't have a degree of freedom there. But for all the other points, you just simply set the value of I in that recipe equation up there. For point I equal 2, you just set I equal 2. So you get T1 minus 2 whatever, T2 times T2 plus T3 equal minus h delta x squared times T infinity, and so on. For point 3, you get T2 minus 2 plus h delta x squared times T3 plus T4, etc. So it's that recipe equation. I'm just applying it at different points I. Okay? So now, you repeat this all the way to the last point, and finally, Tn is equal to T right now. This is a system of equations in T1, T2, T3, T4, T5, T6, T7, all the way to Tn. Those are the unknowns. Is this a linear system of equations in those unknowns? Yes. All of those unknowns show up linearly. There's no T1 squared or sine T2 or whatever. There's none of that. It's a system of linear equations. And what do we do when we see a system of linear equations? We write it in matrix form. And that's how we obtained those initial tridiagonal systems at the beginning of the semester. That's it. There was one step that you guys didn't know at the time, which was how to convert that second derivative into a finite difference approximation. That's the only leap of faith you had to do to get this system of equations, and that's it. You take this procedure. We're gonna do more next on Tuesday. But if you take this any boundary value problem, you have second derivative, first derivatives, and you will get on the exam, you're gonna get an equation with like third derivative and a second derivative and a first derivative. You're gonna discretize that. You're gonna approximate those derivatives with finite differences and write the system of equations. That's the recipe. That's the recipe. You take the ODE, you express the derivatives as finite differences, and write the system of equations. That's why you have to do it every time. That's why you cannot pre-package it, but the procedure is the same. You approximate the derivative with a finite difference formula relating the neighboring points, and you develop the system of linear equations, and you solve it.